pointer arithmetic. First, we'll take a look at the operation of arrays. In this example, I've created an array called message. It's an array of ASCII characters stored within an array of bytes by the data type char. I've labeled the element IDs as a comment above, element labeled 0, 1, 2, 3, up to element 9. And just making a note that element labeled 10 would create the null, would contain the null character. That means that the last element of storage containing ASCII letter is 9. Using a for loop, I'm going to iterate through and print the element ID, I. I'll print out the contents of the element at I, and then I'll print out the address of that element of storage. We should see that each address, the address of each element, is 1 byte apart. Next, I created an array called numbers and initialized them with some small values from 1 to 10. Each element of storage is of size int, meaning that the number 1 will consume 4 bytes of storage. The number 2 will consume 4 bytes of storage. And again, I've iterated through the array. Elements 0 through 9, printing out the element, printing out the contents of the array at element I, and then printing out the address of that element. Let's run that now. Looking at the first section of code, you can see that element 0 contains the letter A. %C is a format specifier to print out the value stored in the array as an ASCII character. Print out the ASCII character printed at element 0 and its address. If we examine the address of each one of these elements of storage, you'll see that the address increments by 1. That makes sense. Looking at the second chunk of code, we've iterated through the array and we found out that each element of storage was separated by 4 bytes of storage. We'll now convert this to using pointers. We'll create a pointer to the message. We need to specify PTR message is of type pointer. If we go to that address, it will point to a char. We'll then initialize that variable to hold the address of the first element of storage. Address of element labeled 0. We'll then print out the I. We'll then print out the contents. And we'll print out the address stored within the pointer. After we have printed out the contents, so we have gone to the value, gone to that address, and printed it out as a character. After we've taken the address stored by the pointer and printed it out, we'll need to go to the next address. Done that using the increment operator. We should see that it behaves the same way. Even though we're using a pointer and dereferencing the pointer, going to the address and printing out the contents, and we're printing out the address stored by the pointer, you'll see that that address is incrementing by 1. Let's modify the second one to behave the same way. This time we're going to create a pointer to the numbers array. We'll initialize PTR numbers to hold the address of the first element of storage. We could use the name of the array by itself, but we'll be explicit. We'll convert this We'll go to the address specified by PTR numbers. We'll print out the contents as a 2-digit integer. We'll then print out the contents held by the pointer or the address. We'll also have to remember to increment that address. Again, we should see that PTR numbers, the number that we print here, should increment by 4. Again, we see the same results. That shows that when we do the increment operation on an integer, again, it reconfirms that the value will increment by a value of the data that we are pointing to, adjusting it by about an increment of 1 here and an increment of 4 here. Rather than incrementing this address, we can have it remain the same. We can keep PTR address pointing to the same value all the time. But instead, we can say, I want to increase the address by a factor of I. And we can also print out the address if we increment it by I. This works very much like an array notation. We're using I to calculate the offset from the base address plus an offset of I times the data type, car. Notice that PTR message is not going to change. We can do the same thing here. We can keep the variable the same, but we can print out the contents by adjusting the address by a factor of I. Notice the use of brackets here, making sure that the address is adjusted before we go to that address. So the address offset is calculated first before we go to that value. We should see the same results. Notice that using PTR pointer, the pointer as a constant, we are just simply adjusting the offset, and the offset is being calculated by the value of the size of an integer. Just to reconfirm that, I'm going to just prove that the pointer is not changing. I'll introduce a printf. The pointer contains %p, comma, PTR numbers. So we'll print out the value of the address. So we'll take the contents of this variable and print it out as an address. We should see that address remain constant. Let's run that again. except I need to put a new line character in there. You'll see that the variable PTR numbers remains constant. We're simply temporarily calculating offset from that base address. So in summary, when we take a pointer and we add a value to it, it's not simply adding the value, it's the value multiplied by the size of the thing that we're pointing to. Works very similar to arrays.